earlier today. So.
Oh, geez.
Yeah, but he records it, so I'm gonna go back and watch it. So it's not a huge deal, but just in case if it does it again.
Oh, is that a real analysis? Or...
Yeah.
Yeah. Okay. All right. It's recording. So, and I'll put this in Canvas afterwards. Okay. So, how is Matlab treating you? Or maybe I should say, how badly is Matlab treating you?
I personally like Matlab isn't the hard part for me. I'm trying to like reteach myself some of the matrices math and stuff since it's been so long since I've done it. I feel like that's slowing me down on the assignment, really.
Okay, so the Matlab itself is not, or it's more. Okay.
Yes, I'm so good on the Matlab part.
I'm sorry, the audio is breaking up pretty badly, but I feel like I'm catching every other syllable.
Well, so far so good on the Matlab part. I'm like echoing for some reason.
Oh, yeah, that happens, and I'm not really sure why. Because it doesn't happen all the time. Did you have prior MATLAB experience? Or
yeah, I did.
Ah,
I mean,
okay.
It has been a while, but yeah, I did.
Okay. I think Taylor, you somewhat had some prior experience, or I know you had a numerical analysis class, so to speak. But
mine was more Maple. We did 1 or 2 with MATLAB, but I never truly learned it.
Gotcha. Okay. Yeah. One of the most widely used numerical analysis textbooks, which is by Burden and Fairs, and it's kind of weird that the book keeps coming out in new editions. I'm not sure what they're up to now, but I've used editions from like the 4th all the way to the 10th over the years because it's so widely used. They both passed away, but so it's like a book happening from beyond the grave. But one of the authors, I believe, daughter is continuing it. They used Maple, and I always found that an odd choice, just because Maple is great for doing symbolic operations, which is literally the opposite of what numerical analysis is about. And that was the first textbook I used here at USM, and since then I've just switched to different ones that use MATLAB before taking 3 years out of my life to write my own. Okay, so all right, so just because of experience, some of you are in a somewhat better position than others, but regardless, I want to make sure that any questions are put out there while we're here.
I just have a question with the ones that you do an im script with. Do you want us to copy and paste the im script into the text file too?
Okay, so in other words, like when there's code snippets in the book.
Mm-hmm.
Yeah. So yeah, because to carry out those problems, you would need that text copied into whatever M file it says. Unless I'm misunderstanding your question.
Like when we turn our homework in.
Yeah.
I don't know why it's echoing.
Okay.
But when we turn the homework in, do we, like for 0.13, I think, we created an im file. And I didn't know if you just wanted the output or the entire im file into the text file that we turn in.
Which problem are you? Which problem are you referring to? I didn't catch that.
I can't hear you.
Oh God. Okay. earlier this week in class, I accidentally muted myself, so I've wondered if I had done that again, but no. Okay, can you hear me?
Yeah.
Okay, you were asking about a specific problem as an example. Which one was that?
Point 13.
So 1.2.13.
Yeah.
Okay. Oh. Okay. Oh, but okay. So that one doesn't. Wait.
That's not the right one. Sorry.
Yeah, I was gonna say that doesn't seem to relate to your question at all.
14.
Right. Okay. Yeah. So for that one, yeah, I definitely want to see the code. For so since you're writing a MATLAB script day in year, I'd want to see day in year.m.
Sorry. So the entire M script, or just like what shows up in the command window when you run day and year?
Oh.
Okay.
Yeah, because so this would be the general rule of thumb for any coding problem. So if there is a M file involved, like as a script, or in some cases it'll be a function, I want to see the M file and an example of output.
Okay.
Let's let you know that when I grade these things, I do look at both. Also, I may just take your M file and run it myself.
So we do the M file separately, or do you just copy and paste it from the text file?
Okay, and now when you say text file, do you mean like like your diary?
Yeah, sorry, the diary.
By the end of the semester, we will be speaking the same language. Yeah, so yeah, it does need to be separate, because it would need to be separate anyway just for you to run it. So it would be sent to me in that same way. What I've done in some cases, I probably won't need to do that in this class because there are only 4 of you. But when I have these kind of problems with grade for a larger class, I actually write my own MATLAB script. So I write MATLAB to grade MATLAB, and it will. Actually, one of these times I should show you an example of one of those where what I do is I create a folder for each student and dump their files in there. And so I'd write a script that would go through all the folders, like go into each one, and then if the assignment called for writing a function, go ahead and call that function, and it would find the function that student wrote. And it would if a student's code generates an error, like it crashes, I can actually write MATLAB code. MATLAB provides a way to intercept that in the way to so that your code that's grading it can still run smoothly, even if the student's code that it calls fails. And so I might I make up a sample input and say, okay, here's what the output should be, and here's the output I actually get. And I'll have my script tell me, yes, they matched. Okay, they get full points, and that sort of thing. Because now it took some time to write a script, but ultimately it saves me time as far as the actual grading is concerned. Okay. Yes. So I may not necessarily run your code, but I like having the option. It does happen sometimes where, and this has happened to me when I was a student, where you go ahead and write your MATLAB code, you go ahead and try it on some examples, and it seems to work fine, and then I might catch a case where it doesn't. So hopefully that won't happen. That can be kind of heartbreaking, as it was for me. But well, yeah, that's the case I was telling Walker about this morning, right? Okay, so yes. Now, just to be clear, I try not to be a nitpicker, especially when it comes to how things are submitted and so forth. So what will happen is that, like, sometimes it's happened where I don't really think of everything, and then I get assignments submitted and I go through them and I find, like, wow, the way the student set this up is really annoying, but I wouldn't expect them to know that. So then I'll just tell you guys for next time. So I don't know if any of you have experienced some of the academic horror stories of having a professor who slices and dices your grade for stupid little things. That's definitely not me. Okay. Well, again, the floor is still yours, so anything you got. Don't be shy.
Is there a way to do, like, I'm trying to think if there's, like, any type of little, like, toolbar or something that we can pin that'll be easier to put in some of these symbols, if that makes sense.
Okay. Wait. What kind of? Okay. What kind of symbols are you referring to?
Just like the basic, okay, like theta, I guess, is a good example. I know that was like one of the first ones, but just because I feel like sometimes I'm searching for ways to still put things in, and I know Maple had a way to like help ease that, and I didn't know if MATLAB had like something like that to make things a little easier.
Are you talking about using things like Greek letters in your MATLAB code?
Yeah, or do I just have to type those out?
Yeah. That ain't happening. So it's MATLAB works in plain text. So if I have a formula that has theta in it, then I'm just going to use some text that symbolizes that, like either spelling out theta or maybe just t. One thing you have to be careful about: certain built-in functions in MATLAB are named after Greek letters. For example, gamma. There is the famous gamma function. So you are allowed to use gamma spelled out as a variable, but that also happens to conflict with a built-in MATLAB function that's also named gamma. All functions in MATLAB, so like its built-in functions, are all named in the lowercase. So you can always avoid conflict of names by using some uppercase. So that's one thing to keep in mind. But yeah, so as far as that kind of working those kind of symbols, that isn't an option. It is possible to include things like that in, like, for example, plots. Like if I want to include Greek letters in a axis label or a title for my plot, that can be done because MATLAB has a built-in, very limited LaTeX interpreter for handling certain text strings like that, but otherwise, no.
Okay. So, that got for some reason. I thought it was all, like you said, like everything had to be formatted, like you have to type everything out basically. I just wanted to make sure that way I'm not typing everything out and you're like, oh, you can just do this.
Oh, for what you're talking about, no, that's not going to happen.
No, you answered like my question, so it makes sense now.
Okay. Cool. Right. Keep them coming. Well, while I'm waiting for anyone else to ask a question, I'm going to put something up there preemptively. Since one of the problems I was asked about was number 14. So writing a script that figures out the day within a year of a given date. So there's different ways of doing that. And now, so this problem is at the end of a section that's on if statements, and it's right before the section that covers for loops. This function, this script, it can be implemented using a very large, cumbersome if statement, or it can be implemented more elegantly using a for loop. Now, and okay, the problem says use if statements. Now, but if you figure out that how it could be done better using a loop, so I'm letting you know that it is possible. I'm also letting you know that I'm perfectly fine with that. So I'm not going to be picky about, oh, you're doing this problem using an approach that wasn't covered yet at that point in the book. I don't care. I'm not going to pull that. So I'm fine with whatever approach you want to take on that. Because all of these things that are scattered throughout the tutorial, they're all going to be useful at one time or another anyway, and you want to be able to use whatever approach gets the job done most effectively. That problem, the other thing is, there's a lot of problems in this assignment, and there are some doozies in here, such as that one. But they're not meant to escalate in difficulty, so it's kind of all over the map there. So certainly the other variation on enter mod gear, which is problem number, the very last one, 29. That is a huge pain, and I should almost apologize for it, for assigning it. So just letting you know, but there are easier ones in between. All right. Nothing more? Out of curiosity, has anyone gotten as far as, let's say, there's 29 problems in total, like up into the 20s yet? Okay, there's a nope, there's a nope. Okay, so I see 3 nopes. Okay, so, and I'll assume Taylor is also a no.
Yeah, that's good for me.
One thing that's very important to keep in mind is that when you're struggling with something, you must avoid comparisons to others, and because often it leads to making assumptions about how your classmates are doing based on your inherently very limited visibility over what's happening with them, and often those assumptions are wrong. And it's like what happens very often in one class or another, where a student tells me, like, I feel like I'm the only one who's not getting it. And I'm like, well, I'm pretty sure no one else is either. Yet, anyway. So chances are, if the boat is rocking for you, it's probably rocking for everybody else. And I think the only time that would not be true is if a student has like some significant advantage coming in. Like, for instance, in this case, someone who's already programming in Matlab for years. I mean, they're going to find this stuff pretty straightforward, but none of you are in that category, so this one's going to be kind of a beast. Maybe I should not have qualified that. Okay, it's a beast. Because what you're doing is that opens the door to becoming overly discouraged. That's not something we want to see here. The whole point for all of you is, wherever you're at now, in terms of your background, is to grow, and that's something that all of you are going to do. Okay, so that's my mini sermon for the day. So what I will do is I I'm going to go through what I had in mind to demonstrate for you, which will involve some MATLAB and some other things. And then there may be some time left, if there is, and we'll see if any questions have emerged in the meantime. Okay, so what I need to do, all right, so I have my document ready, but I may also go to MATLAB, so I want to be able to do that. And okay, so let's get this screen share going. Okay. Can you see my MATLAB?
No.
Ooh. Okay, what's going on here? Oh, the screen share did not actually happen. Why not? That's annoying. Try it again. Okay, yeah, because I figured something was up, but I couldn't see like the red outline. Okay, can you see my MATLAB now?
Yes.
Okay. Oh, there's something I don't need. Okay. And what I remember to do is start a diary before I do anything else. Okay. And I think I want format long for this. Okay. All right. Now, so this is about an interesting look at division when it comes to floating point numbers. So now, when I say floating point, I want to make myself clear about that. In computers, numbers are represented either as integers, and often integers of different sizes. They may be stored in bases that could be as small as 1 byte or 2 or 4 or 8, usually 4. And then there's also floating point numbers that allows for basically decimals, if you can think of it that way, even though it's binary. So if we're working with whatever real numbers that you can. So when I say floating point numbers, that's what I'm referring to. So you can think of it as decimals, even though it's literally a fraction, but whatever. Okay, now, okay. So division is an interesting operation from a floating point number point of view. And I mentioned one other time how of all the operations, the basic operations, addition, subtraction, multiplication, division, division is the most expensive one. And that's why it's been implemented in some interesting ways to try to make it as efficient as possible. Now, first we're going to talk about solving a general nonlinear equation. I really can't type today, worse than usual. F of x equals 0. Now, there's different ways of solving this, but I was going to focus on one in particular. So if we look at a Taylor expansion around some point x naught, so f of x is f of x naught plus f prime at x naught times x minus x naught, and so on. I'm not going to bother with the other terms. So what you can do is you can find an approximate solution of f of x equals 0 by finding out when this is equal to 0. And that is the tangent line approximation. So I'll call this f1 of x because it's first degree. Okay, so just cutting off a Taylor series at this point. So we're going to approximately solve f of x equals 0 by exactly solving f1 of x equals 0. Because here we just have a linear equation, so we can go ahead and solve this easily. I can set this equal to 0 and solve for x. So my exact solution to this being 0, to this equation, so which would be an approximate solution of the original equation, I'm going to call it x1. So that's just going to be x naught minus f of x naught over f prime of x naught. So all I did here was I set this equal to 0, solved for x, and I'm calling the solution x1. So it is the x-intercept of a tangent line. At x naught, whatever x naught I choose. Okay. And what I found is that not just for solving equations, but in some theoretical settings, knowing that this is at least approximate solution of this equation has turned out to be quite helpful. Now we can repeat this process. I can now make a tangent line at x1 instead of x naught and get a new estimate, x2. So now I have an iteration. And this is called Newton's method. Have any of you seen Newton's method in another class? Yes. Sometimes it's taught in calculus. Anyone besides Chelsea? She's the only one I see on my screen for some reason. Okay. Now, and this is quite an effective method, but it also has some drawbacks. But what I want to do here is I actually want to, when it does work, it works really well. I will try this on a specific example. Okay, what's going on here? So I'm going to pick out specific function f. A minus 1 over x, where a is some given constant. It's a positive constant. Now, I want to know when this is equal to 0. I'm going to use x star to refer to the exact solution that we're looking for. What is the solution to this equaling 0? What would x be? Well, I said this equal to 0. So what should x be?
Just over A.
Okay, the audio got garbled, but I believe you said 1 over a. So it's just typical of a is the exact solution to this. Okay. Now, let's look at what the iteration is. So xk plus 1 equals xk. All right, so I fill this in. Okay. So I fill in what the function actually is. So up top, that would be a minus 1 over xk. What's the derivative of this? Well, someone remembers their calculus. What's the derivative of this?
One over x squared.
Yeah. Fill that in down here. Evaluated at xk. But here we're dividing by 1 over xk squared, which is the same as multiplying the numerator by xk squared. So if we simplify this as much as we can, so I'm going to get minus a xk squared. And then I'm going to get minus a minus making a plus xk squared over xk. So I'm going to get another xk. But I'm just going to lump the two together. So simplified fully, we get this. So to summarize, xk plus 1 is equal to 2xk minus a xk squared. We'll compute the reciprocal of a without divisions. So all we need are multiplication and subtraction to actually carry out division. And it turns out that way back in the 60s, a certain random computer actually used this iteration to perform division in hardware. So there was no division circuit. There were circuits for addition, subtraction, multiplication, but not division. It would just do this. So really, it's like the whole operation of division was just made redundant in a way. So what I'm going to do is flip over to Matlab and demonstrate this for you. Okay. So I need to choose a value for a. I'm going to set a equal to 12 because that's my favorite number. Don't ask why. Now, Newton's method requires an initial guess because what we have here in the iteration is we choose an x naught, and then from x naught we'll plug it in here to get x1, plug this in to get x2, and so forth. So we need a value of x to kick this off. So I'm just going to choose one. I'll choose 0.1. Okay. So now what I'll do is, so 112, the exact value of that is 1.0833 repeating. So let's see what happens. So I'll do x is equal to 2 times x minus a times x squared. So from our initial guess, 0.1, well, that's promising. We got the first couple digits correct. So now let's keep going. All right, so one more digit is filled in. The next digit is on the way. So far, 3 digits in total are correct. All right, now we're up to 6 digits. So we went from really like 1 to 2 to 3 to 6 digits. And now a whole lot more. So we're almost, at least to the limits of our display, having exact values. 1, 2, 3, 4, 5, 6, 7, 8, 11 digits correct. One more time. And all the digits that we can see anyway are correct. So, so this worked very well in this case. So the number of correct digits roughly doubles with each iteration. This is an example of what is called quadratic convergence. Another way, so a formal definition, closer to a formal definition, would mean that the error at each iteration is proportional to the previous error squared. So if your error is like 0.01, then you square it to get 0.0001, like 10 to the minus 4, then 10 to the minus 8, 10 to the minus 16. So that error goes to 0 at an accelerated rate, as opposed to linear convergence, where each error is just proportional to the previous error. So like you might see the error decreasing by a factor of 2 every iteration. So in that case, it would take like 50-something iterations to get full precision. But with quadratic convergence, you can get full precision. How many iterations did it take? 1, 2, 3, 4, just 4? Wait, 1, 2, 3, 5 iterations. So we love quadratic convergence because it's so fast. Because you get an idea of, you can just tell that very few iterations, like I said, 5, and you're done. There are algorithms for certain problems where cubic convergence is possible. So in that case, maybe just 2 iterations are enough. But you don't find those often out in the wild. Okay, so that worked well. But now I'm going to do this again, same value of A. With different initial guess. I'm going to pick x equal to 1. Actually, okay. And now I'll carry out the same iteration. So what we get here is something not so good. We got a negative value when our result is, of course, supposed to be positive. And then I keep going. And all hope is lost. So that's one of the drawbacks of Newton's method. You need a decent initial guess for it to work. And if you have that, then great. So what actually happened here? And I'm going to use a graph to show you. So I'm going to produce a graph of the original function, which would be 12 minus 1 over x. So I need some x values. I'm going to call it xx. And I'm going to use this function, linspace, which is useful for generating a bunch of equally spaced values. In this case, well, I want them to be strictly positive. So like from 0.1, I want to dodge 0. All right, so now I have some equally spaced values up to x equal 2, but not quite at 0. Okay, and I'm going to plot the function 12 minus 1 over x. Notice I have a dot here because I'm dividing by a vector. So you're allowed to add or subtract vectors without doing anything unusual. But if you're taking vectors and doing component-wise multiplier, component-wise divide, or maybe raising them to a power component-wise, that's where the dot is necessary before the operation. Otherwise, it will give you an error. So I'll go ahead and plot this. Okay, so there's our curve. But I also want to show you this for negative x. So what I'll do is I'll say hold on. That tells me that you keep what's on the figure. Because if I do a plot after this will be wiped out, but I want to keep it. So I do hold on, and I want to plug in minus x. So I'll just replace x with minus x. And now we see the graph for both positive and negative x. Can you even see these curves over the video feed? Okay, I wasn't sure about it because they're kind of thin. Because what I can do, and sometimes I need to do this anyway, if I click on the arrow here, I can pick out one of these items and I can change its appearance. Like I could, here I've made it a little thicker. I could change the color, that sort of thing. Come on. Okay. All right, so that should be even better. But I also, so I'm going to put in the x-axis also. So I'm going to plot, I have x values from -2 to 2. So plot a line with x values from -2 to 2 and y equals 0. And I'm going to make it black. K is for black because B is already assigned to blue. All right, so now we have an x-axis. And here is the root at 112. Now, I'm going to zoom in on this. So I can click on the magnifying glass here and zoom in on the interesting part of the graph. Okay. So what I did before, actually, I'm going to plot a y-axis also. My y values go from like -40 up to like 70. So I'll put in a y-axis. Okay, so now we have both axes. Now I'm going to plot my first initial guess, the one that worked. So that was 0.1. And I want to plug that into a function. Actually, I'm going to do this. I'm going to make my function f equals, because I'm using that function a lot. So I'm saying this is a function of x. And it'll be 12 minus 1 over x. I'm putting a dot here so I can, if I want to put a vector in here, I can. All right, so now I want to plot 0.1 and f of 0.1. And I'll plot that using a red circle. Okay, there it is. So what would happen is if I make the tangent line at this point and look for the x-intercept, it'll be right around here, close to my exact value. That was fine. But now I'll plot the other initial guess, the one that failed. So 1, f of 1, red circle. Where'd it go? Oh, I zoomed out. I zoomed in too much. Let me zoom out a bit. Okay. There it is. If I take the tangent line at this point and get its x-intercept, look how flat the graph is. It's not entirely flat, but it's pretty flat. The x-intercept is going to be way out here because the line has such a small slope. So that's why it failed. My first iterate was over here. My next iterate was on the wrong side of the graph. And once that happened, there was no coming back. So how can we be sure that we have a good initial guess? Okay, before I answer that question, does anyone have questions about what transpired here? Especially about how these commands worked. Okay. All right. So, well, for one thing, every iterate should be positive. Um, so, um, so once we choose initial guess, if we choose initial guess that's positive. It should be a underscore. When will the next iterate be positive? Well, let's look at what we have. X1 is 2x0 minus a x0 squared. So I want this to be positive. Not greater than 9, just positive. Okay. All right, so now we take a look at this. So I'll factor out an x0, and I have 2 minus a x0. It's positive. Now, x0 is already assumed to be positive, so I need this to be positive also. So what we need is x0. If I set this to be greater than 0 and solve for x0, I get this condition. X0 must be less than 2 over a. Okay. Actually, I'm going to do this. I'm going to write it like this. 2 times 1 over a. Just because 1 over a is the exact solution. So this makes this method seem terribly impractical. That you want an initial guess, but the initial guess relates to the value you're looking for. So it's like, okay, you're trying to find this, so your initial guess must be no more than twice the exact value that you don't know. So how would you have any idea whether this initial guess was a good one or not? It's just relying on what you're trying to find. It seems overly circular at best. So when I worked this out, like the very first time I taught about this method several years ago, I thought, well, this is stupid. Why in the world would anybody use this if you don't even have enough information to get a good initial guess? So I didn't really think about it much after that. I mean, it's cool to show a way to divide without performing any divisions, but as a practical matter, it's like, why? But then, some time ago, over lunch at McDonald's with some faculty, which often happened on Mondays, a now retired computer science professor at USM brought up this method using Newton's method to perform division, and he actually said, in his opinion, that this was the best method for it. Now, like I said, this was implemented in hardware back in the '60s, and it hasn't been done since then. But I thought about what he said. It's like, well, how could this be even a contender for being the best approach when we don't really know what we need to know to get a good initial guess and have a method work at all? But I thought, well, since this was implemented for real, they must have had some way of getting that. And I'm thinking, so I didn't want to dismiss what he was saying, because he must have had some reason. I didn't have a chance to ask him about it at the time. I think I was probably just too gobsmacked at the time. And I thought, I don't know what he's talking about here, so I'm just going to return to my fries. And so then I thought about it later. It's like, well, is there a way to get a good initial guess? And then I realized what he was talking about. Because when you are using floating point numbers in the way that numbers are generally represented, you actually do have more information than you realize. Okay, Okay, so I'm going to get into, okay, I'll just go on to a new page now. Okay, so how are numbers actually represented, like internally? All right, so I'll just refer to my number as x. So x has this form that it's minus 1 raised to some value s times some number m times 2 raised to some number e. So I need to describe what all of these pieces are, s, m, and e. So these numbers, s, m, and e, really define the floating point number. S is just the sign bit. So it's just one bit in the whole floating point number. So 0 means positive, 1 means negative. E is an integer exponent, and that can be positive or negative. And then we have this number m. It's called a mantissa. That's why I labeled it m. So these are the digits from its binary expansion as opposed to a decimal expansion. A good way for you to think about it using something that will be familiar to you is scientific notation. Except you're in base 2. I'll give you an example. If I take, make sure I have my digits right, so I'm pulling an example from the book. Okay. So the number 117. Now, if I were to write this in scientific notation in decimal, it would be 1.17 times 10 to the 2. So 1.17 is a mantissa. 2 is the exponent when in decimal. But the same number in binary would be 1.110101. Whoops. I don't need the parentheses there. Times 2 to the 6. So this is so this plays the same role as this. This gives us significant digits here in decimal, here in binary. Now 2 to the 6 is 64. 2 to the 7 is 128. So 117 falls in between 6 and 7. So that's why the exponent is 6. And these are all the decimal digits. So 1 to the left of a decimal point is still 1, no matter what base you're in. This is raised, this is multiplied by a half. This is multiplied by a 4. We have nothing for 1/8. This is times 1/16, 1/64. Just as these decimal digits, this is 1 times 10 to the minus 1, 7 times 10 to the minus 2, and so on. So these are multiplied by negative powers of 2, just as your decimal digits are multiplied by negative powers of 10. So it's all the same as what you're accustomed to in decimal, but in binary. Okay. Now, in scientific notation in decimal, if you're following a regular convention for it, whatever number you have here would be between 1 and 10. So it can be equal to 1, but always be something less than 10. Otherwise, you should change the exponent. Similarly, this number here, whatever number this represents has to be between 1 and 2. So the mantissa has to satisfy this inequality. So greater equal 1, and strictly less than whatever base beta you have. So 10 in this case, 2 in this case. So this mantissa is between 1 and 2. All right, I know this stuff might be kind of weird. Are there any questions at this point? So let's take a look at our number A from trying to perform division. So A is equal to, well, it's positive, so we won't have anything here. So some mantissa M times 2 to the exponent E. Now, M and E would be known in your code. Then the solution we're looking for, the reciprocal of A. Okay, and I want to emphasize here that the mantissa is between 1 and 2. Then the reciprocal would be equal to some mantissa, so some number m tilde times 2 to the minus E. Now, m tilde is just 1 over m. But the point is, this is unknown. So we know the exponent. We don't know the mantissa of a reciprocal. That's what we're trying to get. But what we can say, because of this, is that it is strictly greater than 1/2 and less than or equal to 1, just by, tilde m. Okay. Just because of this. Okay. So now, it's because we know the exponent. So we don't know what A inverse is. We don't, or 1 over A. We don't know what it is, but we do know its magnitude. And that is actually going to be enough. So this initial guess has to satisfy. All right, so the initial guess is x naught. Whoops. Okay. So x naught must be less than 2 over A. But what is 2 over A? That is 2 times m tilde times 2 to the minus E. Okay. Where if I look at 2 m tilde, I may not know what it is. But what I do know is it's strictly greater than 1, because I'm just multiplying through by 2. And less than or equal to 2. So, okay. So this floating point, so in other words, I don't know this entire floating point number, but I do know that this is pretty much a valid mantissa. And the limits here are slightly different. I have less than or equal to and less than. I have the opposite here. But it covers most possible mantissas that you can have. And then I know the magnitude. So But I need x naught to be less than this. So if my initial guess has to be, I'll put parentheses around this, because this is serving as a mantissa. So because I know that this number is strictly greater than 1, based on information that I have, so I know m, I don't know m tilde. I do know e. Can anyone tell me, based on what we see here among these equations, what would be a viable choice for x naught that would lead to convergence? Anyone care to take a stab at it? So I don't know what this is, but as long as I have something less than this, I'm good. No, okay, I don't know this part. I don't know what m tilde is. Everything else in here is no. I'm sorry, I couldn't hear.
3.
Sorry, that's really garbled.
3 over A. I don't know if it's going.
No, not because x naught has to be less than 2 over a. So, did you say 3 over a? That'd be greater. So
Oh, sorry.
So it can be anything that is strictly less than this. But even though I don't know what this is, I know that it satisfies z's anyway. Anyone else want to take a stab at it? Or Walker, you can try again, of course. I actually don't think I'm going to be able to guess this last 4, but again, that's not.
Wait, never mind.
Okay.
Wait, so it's a number between 1 and 2 over 2 to an exponent. So
Yeah, so all we know about this is that it's in this range. But I just need x naught to be any number that I know for sure is less than this whole thing. And the fact that I know that this part, though unknown, is greater than 1 is key. Any more attempts?
is it just anything less than 1/2?
Sorry, what?
Is it like anything less than 1/2?
Well, that would depend on the value of a. Yeah, because that may not meet this criterion.
Is it allowed to be 0?
Oh no, so it's supposed to be strictly positive.
Okay.
And the trouble is, as a increases, this upper bound gets smaller and smaller. So choosing something, choose something really, really small, but for a certain a, that won't work. All right, Taylor, you're the only one who hasn't put out a guess.
I'm trying to read back through it and see if I can figure it out because my guess was already said.
Oh, okay. We have a little time, so I want to entertain one more guess. All right, so something you know is less than this. And keep in mind, E is known. You do have that. You know you want to be less than this. If you were to take this number and divide it by anything greater than 1, then that would be less than. Trouble is, you can't just pick any number that you know is greater than 1 just because you don't know what this is. So is there something that is greater than 1 you can divide this whole thing by that would leave you with something you know? After you simplify as much as you can.
A two?
Sorry, what?
A two?
I guess 2 is part of the.
Jeez. I don't know what's up with my computer. Maybe a two?
Not just 2.
So you're saying try to get rid of the 2m so that you're left with 2 to the negative e.
Bingo.
Because you know e.
The 2m tilde?
Yeah.
Oh.
Oh.
The initial guess. Because you may not know this, but you know it's greater than 1. So by getting rid of this, because it's greater than 1, this 2 to the minus e is guaranteed to be less than this. So that's why it works. And the thing is, like the exponent you can get from the following: if I take the log, not the natural log, the log to base 2 of a, so that's going to be log of m plus e. Now, m, so the mantis of a is between 1 and 2. So what we can say is that if I take the log to base 2 of this inequality, then I get something between 0 and 1. So in other words, you can take the log to base 2 of A and round down. This notation here, this is you might have seen this before. This is the floor. So in other words, it's the greatest integer less than or equal to this. So I take this number, round down. That's the exponent. Okay. Although the floating point number, since it's represented in hardware, there'll be hardware that can get you the exponent also. I actually can show you, not now, but another time, how to extract the exponent from the bits that make up a floating point number. So it can all be revealed there. So this is actually a practical method in floating point arithmetic, not necessarily on paper. So you have your number A, and so you get floating point representation. Knowing that gets you an initial guess, and you can try Newton's method, this iteration, and after about 5 iterations or so, bam, you have your reciprocal. So I think it's still debatable as to whether this really is the best approach to division, especially since computers don't actually use it anymore. But back then, it was something that was considered worth trying. The last thing I want to mention, since I'm out of time anyway, I mentioned how floating point numbers on most computers have this form because computers generally use base 2. I'd heard about a kind of computer in Russia that used base 3, which I found kind of odd because, I mean, base 2 makes sense because it's all electrical, so 0 for off, 1 for on. So it's something with that 3 states. I'm not sure what that would mean. So I want to find out more about that. So these are off, on, and kind of on. So I don't know. Okay, so unfortunately I've gobbled up all my time, but and I know that at least one of you. Okay, I'm gonna unshare. At least one of you has to get going right away. Sorry, Chelsea. But I will. Well, my next meeting's at 5:30, so I'll stick around in case anybody has any questions about anything. But otherwise, we have to be done. And I'll keep recording until everyone's gone, just in case. But I'm glad he didn't get kicked out, Taylor.
Me too.
Me too.
Okay.
Thank you. I'm gonna head out. We've discussed my issues today already. I didn't get a chance to work further, but
Okay.
thank you.
All right. Okay.
Hopefully I'm not going to echo too bad. But I'm on number 5, the 1.2.5, and like I said at the very beginning, I'm like reteaching myself all the matrices and stuff. So I was just wondering if you could just like give me a hint in the right direction so I know what stuff I'm supposed to be looking at. Like, I retaught myself like the multiplication and scalars and all that stuff, but I just want to make sure I can go in the right way, the right direction with this.
We're getting a random matrix with numbers between -1 and 1.
Yes.
Single random.
It's kind of cutting out. I can't hear you.
How that's happening? Now there's nobody on here. Why there's all this noise? Okay, now you're muted. Can you hear me now? Okay. All right. So you need a random number. So you have a random number between 0 and 1 because that's what rand gives you. So for a single random number, you need a way to like shift and scale. So like basically, you're trying to map the interval 0, 1 to the interval -1 to 1. So if you think of what you'd have to do from that point of view, to like what kind of transformation you'd apply to a single number, you can then apply the exact same transformation to a random matrix, because all you're doing is that would involve scaling a matrix by some number, and then also if there's a shift involved, then you're like adding or subtracting some number to every element of a matrix. So, for example, if I in Matlab, if I have a matrix A, and if I say A plus 1, that would add 1 to every element of A. So you can do it that way. I think I said use the ones function, which you can also do, but not required. So that's really what this is about, is doing this scalar multiplication and addition to a matrix. So I'm not sure if that covers your question or not.
So like, because what I was getting at is like I would try one thing and it's like it's not perfectly from -1 to 1. Like they would either all be negative or all be, you know what I mean?
Yeah.
Does that matter? Or am I like trying to get some negative, some positive?
Can you give me an example of something that you did that gave you like an imperfect?
Well, for me, like the first thing would be just like, oh my goodness, I don't know why it's echoing like that, but like just multiplying by the scalar of like -1, the random matrices. But then that doesn't use the ones function.
Right. So those things. What you did there was you were doing a scaling, but to map the interval 0 to 1 to -1 to 1 involves scaling and shifting. So that involves multiplying a matrix by something for scaling part, but also adding something the matrix to shift every element by something. So really, so it sounds like what this is really boiling down to is not so much what's happening with the matrices, but just mapping of intervals. That how do you, if you have numbers between 0 and 1, how do you scale and shift them to get something that's between -1 and 1. Now, a thing to keep in mind is the size of your intervals. 0 to 1 is an interval of width 1. -1 to 1 is an interval of width 2. So that plays a role here in terms of how you do.
Talking about like just intervals like that. Oh my goodness, I don't think I ever learned intervals, whatever class that was. But like what you were saying, like you would just multiply by 2, right? And that would go 0 to 2, and then subtract 1. That would be -1 to 1.
Bingo.
Okay. So I can do that to matrices. You're
Yes,
saying?
you can.
Okay.
That question gives a lot of people trouble. Oh, can you not? Okay, you're muted now because of the noise. Okay, can you hear me? Okay. All right. Well, do you have any other questions though? Okay. Okay.
That really helped. I muted myself because I couldn't really hear what you had said at the very end there. You were like a lot of people, but then it all started echoing. So I muted so I could hear you.
Oh, I didn't realize that. I'm sorry. A lot of people have trouble with that question.
Thank you.
All right.
Yeah. I think that's it for now, and then I guess I can email you or whatever if I have another question in between now and Monday.
Absolutely. Yeah.
Thank you.